Alright, so we're going to start off, before we get into 7.3, we're going to start with a quick review about what's the difference between p and the mean, as well as standard deviation and standard error. So, on one side, okay, we have the mean, and then we have about how far we expect each observation to be off, which is the standard deviation. So in this case, okay, each dot that we would see, or each bar, would be a single person, okay? Or object. And then the entire histogram would be a sample. Now, on the flip side, when we are looking at p and standard error, okay, what we're looking at is that we're looking at each observation as being a sample. Okay, so each observation is a sample. And then how far a sample is typically off from the population is standard error. So on this side, we're looking at a single person as a dot. Over here, each dot represents a sample of people, and we're comparing it to a larger picture of a population. So this whole thing is not the sample, it's the population. Okay, great. So, moving on into 7.3, what we are going to be doing is we're going to be using something called the central limit theorem. So, whoops. Okay, so what the central limit theorem does is that it says, hey, your survey is good enough that we can actually get a pretty good estimate of the population. But in order for that to happen, we have to make sure that we have low bias, okay, low standard error, and that we can do it over and over and over again. So, and this is only going to be for when we're looking at sample proportions, so that's when we're interested in a certain percentage of a population, so male to female, STEM majors to art majors, things like that. So the first thing is we want to reduce bias, and to do that we have to make sure that our surveys are conducted randomly. This is going to reduce bias. Okay, the second thing is that we need to make sure that we have a large sample. That's going to, okay, reduce our standard error. So a large sample size, which by the way we call n, is going to be large enough that we have at least 10 successes and at least 10 failures. So for example, if we're looking at the percentage of females in STEM, okay, if you are a female in STEM, that would be considered a success, and if you're not a female in STEM, that would be considered a failure. So those are just words. It doesn't actually mean that one is a success and one is a failure. It's just a, are you in the group we're looking at? Are you not in the group that we're looking at? Okay. Condition 3 is that we want a large population. The reason we want a large population is because we want to be able to replicate this survey over and over and over again. So again, the rule of thumb is that we want our population to be at least 10 times bigger than the sample. Now, one more thing is that if you reduce bias, you increase accuracy, and if you reduce standard error, you're going to increase your precision. These are also really good things to remember for your final exam. Now, if we meet all three of these conditions, so we're not biased, we don't have a big standard error, we have a big enough population, what that tells us is that our samples are going to follow a normal distribution where most of our samples are going to have an average value of p . okay, and that they're going to be off by about this much. So what this is saying is, hey, if you have a nice random sample and your samples are big enough, what that means is that your samples are going to be normal. So most of your p hats are going to fall around p, and they're going to be off by standard error. Now, what you should be feeling in your body right now, in your heart, is, oh my gosh, that reminds me of the empirical rule, and you're absolutely right. Now, typically, we don't know if our population is large enough, but we do know if our sample is large enough. Okay? If you don't know the exact sample size, you can just guesstimate. So, gosh, is guesstimate even a word? Guesstimate. So, for example, the population of the world is roughly 7.4 billion. So that's enough. I don't have to know the exact population size. I just need to know it's pretty big. So how do you check these conditions? Well, first, you check to see if it's random by just looking at the researcher's report, okay? Or making sure that we conduct it randomly ourselves. How can we tell if our sample size is going to be large enough? Okay, so we can tell our sample size is going to be large enough by looking at how many successes we're expecting. Okay, and after we look at the percentage of successes we're expecting, we're going to take that and multiply it by the size of our sample. That's going to give us the number of successes. Then we're going to look at the number of failures and multiply that by the size of our sample. Now we want those to both be greater than or equal to 10 at least. Now if we don't know the population value, so we don't know the p that we're looking for, we can just estimate that using p hat. So here's the deal. Suppose that we have 100 people and we're estimating the proportions of females in STEM to the population, and we get that p hat equals 3%. So can we use the central limit theorem? So we want to look at the number of successes, which would be the size of our sample, times p hat, which would be 0.03. So we get 3 successes. So if you're not a success, that means that you are a failure in this class, not in life. So we're going to have 100 times, well, if 3% are successes, then how many are going to be failures? 97%. So times 0.97. So we're going to get 97. So we can't use the central limit theorem because 3 is not greater than 10. Okay? But even though we had enough failures, we still need to have more successes. Okay. So let's check out this next example. So I randomly collect 140 mice from the wild of Washington State. Zoologists say there's about 250,000 mice in the state and that 38% are male. So let's check and see that we can use the central limit theorem. So remember, first off, was it random? So rando, yes, so we know it was random because it was stated in the problem. Okay, I said I randomly collected these mice. The second is, am I going to have enough failures and successes? So my number of successes, well, they said that 38% are going to be male mice. So 38% would be my successes, times, now remember, there's 250,000 mice in the state, but I only collected 140. So that's how many successes I'm expecting to see in my sample. Okay, so 38% of 140 is roughly 53, which is greater than or equal to 10, so we're good. Number of failures is going to be 1 minus that 0.38 times 140, which is going to give me roughly 87, which is also greater than or equal to 10. Great. So, since I can expect at least 10 successes and 10 failures, that means that my sample size is going to be big enough. And the third one is my population at least 10 times bigger than my sample? And the answer is yes. When you guys are checking these conditions on your knowledge checks, I want to see this math right here, okay? Don't just say yes and no, I want to see the math. Now what we want to do is we want to write the normal sample distribution for a sample of size 140 and interpret what that means about a random sample. So, what this means is that I can expect a random sample of mice to contain about 38% male mice, give or take the standard error, which would be 38%, and then if I calculate the standard error, that's going to give me 4.1%. So, here's what this means. It means a random sample of 140 mice will be 38% male, give or take 4.1%. Now, before we get on to question 3, here's what I would like to point out, is remember, this is a normal distribution. So, if I drew a normal curve, I would say, okay, well, most of my samples are going to be 38% mice. It's possible that I see 42% and down to 34%, okay? That's pretty likely. It's also likely that I go up to 46% and go down to 30%. Now, what would you say if I collected a sample of mice and I saw more than 46% were male or less than 30% were male? That would be a very unusual sample, wouldn't it? And the way I got that was using the empirical rule. So let's just keep that under our hats for right now. So, the next question says, what is the probability that I collect a sample of 140 and the sample proportion is less than 44.15% male? Okay, so again, we're going to draw this guy out one more time. So remember, in the middle we're going to have 38, 42, 46, 34, 30. And it's asking, what's the probability that we have less than 44%? So we're looking at all of this stuff over here. So since this is a normal curve, I can kind of act like this is my average and that my standard error is like my standard deviation. So what I'm going to do is just like I did in chapter 6, which is I'm going to find the z-score. So I have 0.4415 minus my average. So on average, I expect my mice to be 38% male, divided by my standard error, or my standard deviation, which is 0.041, which is going to give me a z-score of 1.5. And if I check on my z-score table, so if I look at my z-score table, that's going to give me that the probability that I see a sample that is less than 44.15% male mice is going to be 0.9332, which is that I have a 93.32% chance of seeing that. All right. Great. Let's look at a couple more examples and then we'll call it a day. Remember, when you're doing the z-score and the probability, you can do that on StatCrunch too. That's totally fine. So, for the last example, suppose that we have a tight race for mayor between candidate A and candidate B in Port Orchard, and the vote is split 50%. So what we do is we take a random sample of 1,000 voters and ask who they will vote for. Okay. Note that the Port Orchard population is around 10,000. It's actually more like 14,000 now, I think, but it's big enough is what we're trying to get at. So, here's my question, is what percentage of the sample should we expect to support candidate A? So, we should expect P hat to be 50%. So we expect our sample to mimic our population, so we'd expect 50%. Okay? Now, what is the standard error of the sample proportion? So the standard error is going to be the square root of 0.5 times 1 minus 0.5 divided by our sample size. Remember, we have a sample of 1,000. So our standard error is going to be 0.0158. So can we, it says appreciate, but it should say approximate the probability that the sample proportion will fall within 2 standard errors of the value? Yes, we can. That's by the empirical rule. That would be a 95% probability. Okay, so for the next one, according to an article from Huffington Post, some experts believe that 20% of all freshwater fish in the United States have such high levels of mercury that they're dangerous to eat. So suppose that a fish market has 250 fish, which we consider randomly sampled from the population of edible fish. Okay? First, we want to show that this satisfies all 3 conditions of the central limit theorem. So first, rando, yeso. Why-o? Because it said so, randomly. 2, are we going to have enough successes and failures? So, for successes, we have 250 fish times, we expect 20% of them to have high levels of mercury, 0.20. And for failures, we have 250 fish. And if you're not in the 20% of successes, then you're going to be in the 80% of failures. So we expect to have 50 successes, and we expect to have 200 failures, which are both greater than 10, so we're looking good. Now the third thing is we want to know, is the population of freshwater fish greater than or equal to 10 times our sample? Now, I don't actually know the exact population of freshwater fish in the United States, but I would not hesitate to say that it is much bigger than 2,500. So I'm going to go ahead and say that that is also true. Now, since we met all the central limit theorems, what that means is that we're going to have a normal curve where most of our samples are going to reflect the population, give or take a standard error. And remember, since this is a normal curve, we can use the empirical rule. So let's approximate the probability that the fish market will have a proportion of fish with dangerously high levels of mercury that is more than 2 standard errors above 0.2. Okay? So remember, if we go 2 standard errors out, okay, that means that in the center we have 95% of our samples will probably fall somewhere in here. So what's the probability our sample has more than 2 standard errors above that 20% proportion we had? Well, that's going to be 2.5% by the empirical rule.